John Nicol, longtime Eterna player, developer, known in the game as J Nicol. And I'd like to talk to you about one of the labs that we worked on. That's the Pseudoknot Detective. If you go to the Eterna menu, you can pull it up by going into the labs. But right here, we have the Pseudoknot Detective. And if you go into the labs, and then I'll just go to review. Here you can see all the different designs that all the players had input. And I'm going to look for my name. And I'd just like to pull up, I'm going to order it by the score that we have received. And I just want to pull one up as an example for how we did the padding. You can see for this sequence itself, we have the control sequence, which is the area of interest from 229 to 265. If I actually look at this, (229) to 265 would be this area right in here. I don't know if I put the numbers on, if it'll be too busy, but you can see 229 is right about here. And then 264, I believe, was the control area. So this is basically the sequence that we were looking to test. We want to see, we got a list of control sequences, 642 to be exact. And we wanted to go through all of these sequences to see if we could pull out pseudoknots that are known or predicted to be within these structures. So the job that I had was to put in padding all along this side. And what we wanted to do is put in hairpins so that it would not interfere with anything else within the structure. So the goal we want to do is make sure this area right here, the area of interest, I'll call it, does not interfere with any of the padding that we put in. Also, the barcode, the tail, and the head sequence, we also do not want interfering. So I guess I can go to this is, you can see this screen, right? Okay, I'm going to assume that this is the list of sequences that was found by Jill Townley, and I believe Eli Fisker helped her out with to actually compile the PDB and the PDK sequences.
I don't think we see this list.
Oh, you don't see it? That means I have to do a new
I think
share.
you just shared the one window.
Yeah.
Now I see it.
Okay, great. Sorry, kind of new to the Zoom sharing. I think I need a new share every time I go back and forth. Okay, so this is the list I was given. Basically, Jill and Eli came up with a list. And I really need to get rid of this screen here. Okay, we can see that in this list we have 400, I believe, well, 399 sequences in the PKB database. And in the PDB, we have 243 sequences. I'm subtracting out the header, so this is a total of 642 sequences. So we can see this is the sequence, or I should say sequence of interest that we're looking into that we believe will have a pseudoknot that we are interested in. I'm just going to try another. Okay. Sorry about that. I'm just trying to make my way here. Are you able to see this flow chart that I have up here, or do I need to share that also? Okay, I believe this
All
will
we're
do it.
seeing is your header.
Okay,
There we go. Now we see the flow chart. Great.
okay. Okay, so basically, I wrote a JavaScript program in our scripting services. The scripting services allows you to write a lot of different things. This was written as a booster. And if anybody's interested in what the scripting area can do, I mean, I would suggest to talk to Astromon. He's been very good with talking with the players in chat to find out the different scripts and how to use them. This particular script that I wrote is a booster, which means that when you go into the Eterna game, you can pick up a list of different items that you want to run within the game. So what I did was I wrote a JavaScript booster as a script, and those 642 sequences are put in that. Basically, I copied them into the script. Within that script, I read each one of those individually. And then the first thing we do within that is to choose a barcode. That barcode itself does not have any rules except that 60% is a GC and 40% would be an AU base pair. You could also see from, I could go back to the original, but I don't want to go back to the lab at this point. But in the lab, you also have the hairpin has to be UUCG. And so what I did within this barcode is just pick out that 60-40 mix. Okay, within that mix, the next thing that we do is we're going to find the length of the padding. So the sequences that we have that we pulled out from the databases, the area of interest ranges from 21 bases up until, I believe, 219, 220 bases. So what we want to do is find a some sort of an algorithm to put that padding in so it doesn't interfere with the rest of the bases that we have put in. So what we did do was we came up with a specification. Specification in the early stages, we basically said we want to put in hairpin stems hairpin stems that used 5, 6, and 7 base pairs with 2 to 3 linking of an A or AA between each one of these hairpins. Based on Jeff Anderson Lee's suggestions, we basically revised that to say we want to use hairpins of 7, 8, or 9 base pairs and either use 1 or 2 AA bases, unpaired bases for linking between them. Okay, after we did that, I'm going to go into these rules a little bit more later, but I wanted to give you an overall of how we came up with this. So what we do is we take the header, which is basically fixed. If you look in the puzzle, you see that's locked bases. So we're going to take the header, we're going to add the padding to it, and the area of interest, the barcode, and the tail to come up with a complete sequence. What we wanted to do was try to put the area of interest at the end of the padding and right before the barcode. And you can see in most of the designs, this is true. There are some exceptions. I'll go into that later, but this is the preferred way of doing it. we're going to fold the sequence using Eterna thresh knot. And Eterna thresh knot predicts pseudoknots, and it's a fairly fast algorithm for us. So basically, the entire algorithm here is going to bend on what the structure we get out from Eterna thresh knot. And in Eterna thresh knot, once we do the folding API, it'll give us out a structure. In that structure, we want to look for interactions within the rest of the areas that we had added. So in other words, from this entire sequence, we want to make sure that the header does not combine with anything else. We want the header to look exactly the same as the header area. The padding, we want it to remain as all the hairpins. Area of interest, we don't really care about. We're going to let that fold up however it wants to. The barcode needs to remain as the barcode we selected. And the tail, we want to make sure it doesn't combine with any other place within the nucleotides that we have selected. Okay, so that's what I mean by we check for interactions. If we check for interactions and we see that everything has folded in the expected way, basically the header, the padding, the barcode, and the tail are what we expect it to fold as, will continue. So basically we're saying if there's no interactions, we're going to save it as a properly folded sequence. After we get 20 properly folded sequence from this one area of interest, what we're going to do is perform a base pairing probability. If we don't get 20 sequences, we're going to cap out at 5,000 tries. Basically, this is a long time. This takes probably about an hour or so to run through because it's a lot of tries. The folding algorithm takes a couple of seconds per each try. So that's why I had to cap it at a certain amount. What we're going to do is take pairing probability, and the pairing probability, I'm not sure if I did it in an acceptable way or not, but basically what I did was I looked at each one of the base pairs of the areas that were known. In other words, I just looked at the header, the padding, the barcode, and the tail. And I looked at the worst possible base pairing out of that. I saved the worst possible pairing and then compared the next sequence. If the next sequence had a better worst pair, then I would save that as the best selection. So basically, I'm just looking at the worst pair out of what we expect to fold correctly. After we've gone through all of the properly folded sequences, we're going to take that sequence and submit it to lab. After that, we're going to go through all 642, and we're going to save those to the lab. So in the Pseudoknot Detective lab, you'll see that the solutions that I have submitted, there are 642, which correspond to all of the selections that we see that we put in there. I'm going to try to go new share. Okay. This is a little bit more in depth into that padding diagram that I had put in. What we want to do for the actual padding is we're going to try to use 7, 8, or 9 base pair hairpins. The closing pair stems for both ends, for the end that is the first base pair coming in, the closing pair, up until the tetra loop, we're going to have both of those base pairs to be a GC or a CG. all other base pairs within that stem are going to be randomly chosen. And the randomly chosen base pairs is going to be 50% GC, 50% AU. For the tetraloop hairpins, we also randomly choose one of these hairpins, UUCG, GUGA, UACG. Basically, originally, we wanted to use just the UUCG, and I had suggested the GAAA. Jeff Anderson Lee had said he had really good results with these two hairpins also. So what I did was I mixed these three different tetraloops into the designs. So what we did was we combined these hairpins based on these set of rules. And when we did the base pairing probabilities, you may see a tendency for one or another type of hairpin to come out, or for the number of linking A's in between. We said in between each hairpin, we want to have one A or two A's in between each hairpin. And we want to try to keep the area of interest at the end of the padding just before the barcode. So these were basically the requirements that we want to have. Now, some of the reasons we can't really have all those requirements is because of this chart. Depending on how many nucleotides there are, for instance, if we have so many nucleotides that we can't put any hairpins in here, we don't want to put any stems lower than a four-stem hairpin. So what we did do is said anything between 1 and 12, we're just going to leave as unpaired bases, and I'll randomly select what unpaired bases that we'll put in. If we see that we want to pad it with 13 or 14 different bases, if that's how many nucleotides are left over, we're just going to use a 4-pin stem, 4 base pair stem, and use up the rest of the padding with just the 4 stem. You can see the same works for 5 and for the 6. You can see in between there's kind of weird numbers that you can't really fit a 7-pin in here without using maybe like a 5 and a 7 or a 4 and a 7 combination. So we felt it was best to use 6 base pair hairpins instead of like doing a mix and match of 7 and 4. So basically, if we have this number left over, we're kind of forced to use 2 6 base pair hairpins or 3 base pair hairpins. If we get within these areas, like 19 to 20, 21, 22, we know that we can use our preferred 7, 8, or 9 base pair hairpins. So if we're saying 38 through 48 needs to be padded, we know we're going to have 2 hairpins, and we can have a mix between these guys to get that. So in other words, if I used a 7, if I randomly chose a 7, I'll probably most likely have to have a 9 for the next one. If I chose an 8, I'll probably have to have another 8 to fulfill this requirement. If you go a little higher, then you have more of a leeway to be able to choose what different hairpins you want. If you go from 76 to 96, you can see we'll have 4 hairpins. And you can see 95 overlaps with the 96. So within here, if you have 95 or 96, you can either have 5 or 4 hairpins. And we're basically randomly choosing the first couple right here. But as you get to a smaller and smaller number of nucleotides that are left over to be able to be padded, we're going to fall in one of these categories. So we're basically choosing these categories so that you have to, like if you choose a 5, it'll fall back to be within this number of base pairs for a 4. If we choose something within here, it'll fall back to be within here for 3 more hairpins. So what I did was I chose one hairpin at a time, built that up, and said, okay, how many more hairpins can we include within the padding? So this chart basically is telling you if we start out a certain amount, you can keep falling back within the 7, 8, and 9 pairs that we want to use as our requirement. If we start out originally between these numbers, we really have no choice but to use a 10 pin, a 10 base pair hairpin. Within this choice, it's 11, 12, 13. And if we happen to have 33 nucleotides that need padding, we're going to have a 14 base pair hairpin. I guess there's other combinations we could have done. We could have said, okay, we'll have like for this, we could have had like a 7, 8, or 9, and then use the rest as unpaired to have it fall back in here. That's one other option we could have done. But the way we built the system, this is how we actually did it. I think that's all I have to say about how we padded this piece. Let me see if I had any more notes I wanted to show you. I think I want to go back to, I want to pull up the lab itself because I wanted to show some things within that. Let's see how we can get there. Okay, so I just wanted to point out a couple of things from this. I mean, that's our ideal that we have. I want to go back to sorting it by, oops. Sorting it by ID. Okay, this shows you a list of how I entered each one of these different sequences. So this very last one here is the last one that was actually put into the system. I can see right here that it has experimental structure of, and then it just has dot. So I'm going to say that I did have an issue with the script itself. And in the script, when I folded a lot of sequences, basically we have 600 of them. When I started folding a lot of them, I had some memory issues. In these memory issues, it would just give me errors and I couldn't continue any more sequences. So what I did was I chopped the sequences submitted in half. So I submitted half at a time, then I came back and submitted the other half. I think having this of a blank right here kind of means I'm starting to hit a memory issue because it should not show that. It looks like the first or the last 120 of them were giving me that error. If I come here, an experimental structure of, and then you can see this structure right here, we know that there is no memory error that I ran into. The next thing that I wanted to show is, you can see here, I put control sequence at base. And you can see everyone that shows the 264 at the end shows that it was placed right before the barcode. When we start out at 36, it tells me that this was a very large sequence for the area of interest. So we didn't really have that much space to be able to put the padding in itself. So with this padding, I'm going to assume it's all unpaired bases because we couldn't fit a barcode. We couldn't fit a stem at this point. So if you go down a little further, you can see one of these right here, we probably were able to fit a stem. And I'm just going to go here to try to verify that. So you can see we have the barcode right here, and the area of interest would be from 82. Actually, we have two barcodes. So if I take this off, it's a little easier to see. We said starting at base 82. I just want to see where that base is. Okay, so base 82 is actually right here. I don't know if I marked it or not, but it looks like we have 3 hairpins in here before we have the actual area of interest, and then we have our barcode. You can see Eterna Thresh predicts that we should have these hairpins. The area of interest, we don't really care too much what it'll look like. We have the barcode and the tail. You can see nothing is being interfered with, which is one of our criteria. I'm going to go back to the browser. And when we hit different spots in here that do not say, oh, here's a 233, you can see this is one of the sequence we probably had issues with. If I put this sequence back near the barcode, right in this area, then we were having it interfere. So what I had to do, and actually this is even a stranger case, where we have from area 27, which is base 27 here, to 233, I believe is like right in here. So this is the area of interest from here to here. And this is where we wanted to put our padding. You can see I don't have a hairpin there. And one of the stranger cases that we had was if we do put hairpins here, it seemed to interfere with either the barcode or the header tail. So what I had to do in the code, I went through and said, hey, if I can't put the area of interest right at the end, try to put another hairpin in between it. And sometimes even when I did that, we still couldn't get good results. So I said, turn that hairpin just into unpaired bases. So all of this happens to be a sequence that I submitted with unpaired bases right in this area. And it happened to come out as one of the better pairing probabilities. So this is the one that was finally submitted. Is there anything else that I want to point out within this? I think that's basically all I wanted to point out with how we did the padding and how we submitted. You can see like one of them in here was really crazy. So this must have been a really hard sequence to get not to pair with the header or the tail. And each time we put this in, I was changing the barcode. So I didn't reuse the same barcode for like all 20 possibilities. Every time I would update the barcode and I would update a new randomized pairing. So for this guy, I can see just by looking at where the control sequence is, it was very difficult to find something that did not pair with the rest of the structure.